All right, everybody, this is the first video for our new unit and really new section of physics. We're moving away from sort of mechanics, motion of things, into electricity, which does include motion, but not of things like we think. We're actually going to start talking about the motion of subatomic particles, electrons, protons, and neutrons, mostly electrons. But in order to talk about electricity, we have to first start with electric charge. And this idea of charge, that you have positive and negative charges, came from Benjamin Franklin way back in the colonial times and sort of during the revolutionary times. He was one of America's greatest scientists, or he certainly was the greatest scientist at the time. I mean, you could make arguments for other people, but I think, at least for that time, he was the best in America and maybe the best in the world. He did extensive research into electricity, what it was, how it worked, the famous sort of kite experiment where he flew a kite with a key on it up into basically a lightning storm and realized that he could store this lightning on the key, if you see in the picture here. But ultimately, his main contribution, or one of his main contributions, was that there are actually two types of charge. Previous to him, the idea was that sort of electricity or lightning was made up of these two completely different things. And he said it's really just one thing, but there's just two sides of it. And he called these types of charges positive and negative. And this naming doesn't really mean anything. There's nothing about them that's positive. That's greater than one or less, or I'm sorry, greater than zero or less than zero. It's just he wanted to show that they were opposites. If we had said instead that it was the magenta charge and the cyan charge, or the red and the blue charge, or whatever, it's just a naming convention. It doesn't mean anything actually about it. We just say that there are two types of charge, positive and negative. And this is an idea that's likely pretty familiar to you. You've heard of these positive and negatives, or you've seen magnets with a positive pole and a negative pole. They're very similar. And the other thing that he realized was that positive charges repelled positive charges. So like charges repel each other. If you take two objects that are charged with a positive charge, or that are charged in the same way even, and you put them next to each other, they push away from each other. And that was sort of how he realized that there was certainly one type of charge, and it repels. But if he charged objects in a slightly different way, if he had a positive and a negative, if he had opposite charges, they repelled. I'm sorry, they attract, not repel. So opposite charges attract. The fact that he could do basically the same thing, he could charge these objects, but sometimes they would repel, sometimes they would attract, meant that there had to be two sort of sides to this. And he said that calling them positive and negative. And in order to really realize what's going on with charge, we have to understand a little bit about the atom. And a lot of you have seen, at least at one point in your life, the atom. The important things are that they are made up of protons, neutrons, and electrons. We say that protons have positive charges, neutrons don't have any charge, and electrons have a negative charge. So because the neutrons don't have any charge at all, we get to leave them out. I mean, they're important for other things, but for us, the neutrons are not going to be important. We're really only worried about the protons and the electrons. And these make up atoms. This is a terrible drawing here of what an atom looks like. It doesn't actually look like that at all. But we have this center, a very positive center. We call it the nucleus. It's got the protons and the neutrons. But around it are these electrons that swirl about. And the protons and neutrons are relatively locked in there. They're pretty tightly locked together. They don't like to move, but the electrons get to move around. And when we talk about charge happening, we're talking about the movement of electrons onto or off of an object. If we gain electrons, that means we gain a negative charge. If we lose electrons, we gain a positive charge overall. So if you lose a negative, you gain positive. And the smallest unit of charge that we can transfer is the charge on an electron, or the charge on a proton. The smallest unit of charge that can be transferred, we call this the elementary charge. We represent it as the letter E. Protons and electrons have the same amount of charge on each one of them. So it's for both of them, but remember it's the electrons that move. So we either call E for the positive charge on a proton or negative E the charge on an electron. And that's great for sort of counting how many charged particles we have on a particular item. But for our calculations, we have to use what are called coulombs. And one electron is equal to 1.602 times 10 to the negative 19th coulombs. So let's say we wanted to calculate the charge on a particle that contains 150 protons, 300 electrons, and 200 neutrons. First, we need to find how many elementary charges are on this object. Which do we have more of, protons or electrons, and how many extra do we have? So I'll say, all right, my protons are my positive charge. So I'll say that we've got 150 positive E charges, right? 150 protons, that means with those, there is 150 elementary charges that are positive, but I'm also going to add to that all of my negative charges that are on those electrons. I've got 300 elementary charges there. And I make sure it's a negative because the electrons are negatively charged. So when I get done, I get a overall or a net charge of negative 150 E. So that just means that I've really got 150 more electrons than protons. That's really what I'm trying to say here. But if I want to do calculations, I've got to be in coulombs. That's my SI unit. So I'm going to do a conversion. I'm going to say that negative 150 E, and then I'm going to set up an equality like we've done before. I want my E's to cancel, so I'm going to say that 1E is equal to 1.602 times 10 to the negative 19th coulombs. Multiply across the top, divide by the bottom, and I think we get somewhere around 2 times 10 to the negative 17th-ish. I don't have my calculator with me, but I think that's what we come out to. Let me double check here. 1.6 E negative 19 times 150. It's about 2.4. Yeah, we'll drop that 4 in there. 2.4 times 10 to the negative 17th, and that is coulombs. That is our unit for charge. So make sure that you're able to make that conversion. One of the ways that we can charge objects is by rubbing two objects together. If you've ever taken a balloon and rubbed it on your hair and then you realize, oh, I can make my hair stick up, you charged an object. You ripped electrons off of either your hair or off of the balloon and passed them to the other object. This is known as the triboelectric effect. You don't have to know that name, but I think it's kind of cool to know. The electrons are transferred though. When we rub objects, we are stripping away we're stripping away electrons from whatever object. We are not moving protons. If we move protons, we get a nuclear reaction, the same stuff that goes into making atomic bombs. We look for nuclear reactions there, and we don't want that in your everyday classroom setting or whenever you're trying to just plug something in. It's the electrons that move. That's the biggest thing here. And when those electrons move, we can't lose any. We can't lose any electrons. Electrons are conserved. They are matter, and matter is conserved in the universe, which means that charge is also a conserved quantity. Just like we've had with momentum, with energy, we've seen this concept of conserved quantities come up again and again in physics. It's one of the sort of overarching ideas of physics, that there are certain things that are conserved. You can't change them. So let's say I had two perfectly neutral objects. Neutral just means that they have a balanced charge. The number of positives and negatives, protons and electrons, are equal. So I've got a 3 proton, 3 electron particle here, and I've got a 1 electron, 1 proton here, and they both have charges of 0 E, right? They both have perfectly neutral setups. But let's say that these two objects rub together, and I stripped one of those electrons away from this positive proton there. What I would end up with is 4 electrons on this 3 proton object, so I have a -1 overall charge, but that extra electron had to come from somewhere. If I'm going to gain an electron here, I've got to lose it from somewhere, and I lost it from that one proton. So I end up with a positive E charge there. I've got an extra proton compared to my electrons on that object. And if I add these two numbers up, a negative E and a positive E, I come out with 0. Whatever total charge I started with, I also have to end up with. If I started off with two neutral objects, my two charged objects at the end have to add up their charges to still be 0. So when we transfer charge this way, when we rub two objects together, or really whenever we transfer charge, whether it's by conduction or induction, or really just conduction, I should say, and we'll get to that in a bit. But when we transfer charges between identical objects, we split those charges equally. If I have two objects and one is charged and one is neutral, so let's say that I've got a 10 coulomb sphere here, and I've got an identical sphere here, but it's got a 0 coulomb charge on it. If I touch these two objects together, what I end up with is two spheres that both have 5 coulombs on them. They split them equally. They split those charges equally. I still have to add up to be 10 coulombs because that's what I started with, but these two objects have to be equal. So a different example with that, let's say that I had one object that had a negative 3 coulomb charge and an identical object, but this one had a 5 coulomb charge. My total number of coulombs here, if I add these two together, I'm left with just 2 coulombs positive. 3 of those negatives cancel with 3 of the positives, and I'm left with just 2 coulombs. I had 5 plus negative 3, and that gave me 2 coulombs. So if I'm going to split those 2 coulombs equally, when I get done, both of these objects have to be left with just 1 coulomb. Because 2 was my net charge, I split that net charge in half. I split it equally. All right, and that really ends sort of the intro to this unit. In further videos, we're going to talk about conduction and induction, different ways of charging objects, as well as electric force and the electric field. So hope you keep following along for those videos as well. Thanks for watching.